Let's wait for the recording. Okay, so hi everyone. Welcome to the South American Geometry webinar. This week we're going to have Daniel Fadel, who did his PhD here in UNICAM, then a number of postdocs, IMPA, previously in France, and now soon to be faculty at the Federal University of Rio de Janeiro. He's going to be telling us about the flow of geometric structures. I should say that if you wish to, we're having trouble recovering the instructions. Okay, so at some point during the talk, you will find in the chat instructions to join our mailing list, our scheduling system for the seminar on the Google agenda, as well as the link to our YouTube channel for previously recorded talks, and also the links for future talks during this term. So Daniel, without further ado, can we do 50 minutes plus discussion, if that's okay?
Yeah, I'll try.
Right. Okay.
So thank you very much, Henrique. Thanks to the organizers for the invitation. I think it's the second time I speak on this seminar, so always a pleasure. Today I plan to talk about these harmonic flows of geometric structures. This talk will be based on joint work with Andrés Moreno, Éric Loubeau, and Henrique. So let me begin by telling you what I mean by a geometric structure. So I will review some base terminology and set up the notation. So first of all, M will always be a connected, oriented, smooth n-manifold without boundary. I will denote by this the frame bundle, the principal GLN frame bundle of M. This is, so of course, the standard action here is just, can you hear? Okay, so can you see this? Yeah, so I'm assuming that the right action here is simply doing this, right? Composing with this coframe. H being a Lie subgroup of a GLN, an H structure on M is just an H reduction of this principal bundle. So just a principal H subbundle. And the existence of such is purely a topological question. So, well, for those of you that are not so familiar with this, let me just put a small list of groups H. So for H being the connected component of the identity of GLN, an H structure is simply orientation on your manifold. And the existence of such is obstructed by the first Stiefel-Whitney class of your manifold. And so when this vanishes, you know that this structure exists. And actually, I'm assuming orientable, so I'm assuming this is vanishing. So there's always, I can always pick an orientation. For H, let's say ON. So this is an ON structure is just equivalent to a Riemannian metric on your manifold. And this always exists. Let's say for G2, a G2 structure is simply a positive three-form on your manifold, meaning a three-form which point-wise is linearly identified with the canonical three-form given by octonionic multiplication between U and V, inner product with W, where this I'm thinking R7 here as imaginary octonions. This is just the standard flat metric. And the existence of such is obstructed by first and second Stiefel-Whitney classes. So the manifold should be orientable and spinable. And one last example. Let's say when H equals the trivial group, then this is, well, an H structure then is just a global section of your frame bundle. So it is just a global frame for your tangent bundle, and this exists precisely when this is trivial, right? So there will be more examples throughout the talk, but just to give you a few ideas of what we are going to talk about. So yeah, so an SON structure then is just equivalent to a Riemannian metric in orientation. And in fact, so the SON structure is just then what we call the frame bundle of oriented orthonormal coframes. And I will denote this by this frame of MG. We shall restrict to H structures which are within the realm of Riemannian geometry. So H will always be, from now on, a subgroup of SON, which I will further assume to be closed and connected. And then any H structure, of course, induces a unique SON structure containing it. So this means that any H structure now induces a unique metric in orientation compatible with this further geometric structure that we might have coming from the subgroup H. But nonetheless, note that there are many H structures inducing the same metric in orientation, right? So note that the group H acts freely on this principal bundle, being a subgroup of SON, and the quotient map is a principal H bundle in its own right, and then the map closing the diagram, this map pi, is a fibration, again, locally trivial fibration, which is actually, you can identify it with the bundle associated to the frame bundle of oriented orthonormal frames with these homogeneous fibers, copies of SON mod H. And so there's a bijection here between compatible H structures. So if you fix your SON structure and you look at H structures inducing that SON structure, then there's a bijection between these and sections of this bundle pi. So what you do is just create so out of a compatible H structure, you create a section that at each point projects with this projection pi H any frame in the fiber above any oriented orthonormal frame at the point X, which is in your reduction, because any two of those will differ by an element of H, and this projection here doesn't see this ambiguity, so this is well defined. And then conversely, given a section here, you just take you just embed the manifold through the section, and then take the prime image to this projection here, you get a compatible H structure. Right, and so as I will be assuming H to be closed and connected, so as I mentioned, this is a homogeneous space, which is normal and with this canonical bi-invariant metric. So I will just need one fact coming from this, which is when you decompose the Lie algebra of SON and the Lie algebra of H plus the orthogonal complement with respect to the bi-invariant metric, this decomposition is, so the H is invariant under the adjoint representation. And so if you have a compatible H structure on your manifold, which already has a fixed SON structure, then there's an H module decomposition of the bundle of skew-symmetric endomorphisms, So you can simply, so this in the Lie algebra level goes up to this decomposition here, and this is well defined precisely because of this condition. And so you have, so fiber-wise, at each point, the endomorphism breaks into those that in a adapted H frame is an element of the Lie algebra of H, and or those with that are elements of the Lie algebra of M. Sorry, this complement M. And then, so let me just remind you that a compatible connection, so given a linear connection on the tangent bundle, it is compatible with a given H structure, or if the H structure is fixed, we say an H connection, when its corresponding connection one form reduces to Q, so to Q, sorry. And these are precisely the connections coming from this principal bundle Q. And since Q is compatible with G, so it's an H structure compatible with this metric G, then such connections should preserve G. And so if we compare it with the Levi-Civita connection of this metric, so the difference between two connections is an endomorphism, and both connections are metric preserving. So this endomorphism actually is skew-symmetric. And being a skew-symmetric endomorphism, you can project, so you have two components, the H component and the M component. So taking off the H component of this connection here, by the way, I just picked any H connection on TM, and this exists because Q is just a connection coming from Q, and any principal bundle admits a connection. And so if I call this new connection nabla H, you will see that it is the unique H connection on M with the property that this tensor here, this difference, lies on this component of the skew-symmetric endomorphisms. Because any two H connections will differ by an element here. And so if two of those have the property that the difference lies in M, so the endomorphism relating then is 0. So there's a unique one with this property. So this tensor T here, which is a one form in M with values in this M part of the endomorphisms, the skew-symmetric endomorphisms, is just what we call the intrinsic torsion of the H structure. And we see that the H structure is torsion-free, meaning this torsion tensor vanishing identically if and only if the Levi-Civita connection is an H connection. And this means that the holonomy of the metric, the Riemannian metric that you are considering, is a subgroup of H. And well, so there's this list of Berger dating back to 1955 I mean, up to simplifying assumptions that take off ambiguities. And so if you assume your Riemannian manifold is simply connected, irreducible, and non-locally symmetric, then there's a table of possible holonomy groups for this metric. And apart from the SON case, all of the other groups we call maybe the special holonomy groups, and these are very interesting, very rich geometry comes from these. But to find torsion-free H structures is, well, so to find H structure is just a topological question, but to find torsion-free H structures is a much more difficult problem. And there's, for some choices of H, we don't know yet sufficient topological conditions for a manifold to admit torsion-free H structures. And well, so our aim here will be to talk about, so we'll just recast this language of H structures to tensors, because at least all of these groups of Berger's list are always subgroups of SON, which are stabilizers of a finite set of tensors in Rn. And then for these, in these cases, you can reduce your H structure to be just simply a collection of tensors on your manifold. So let me precise that. So given an H structure and a tensor field on your manifold, we say that this tensor field is stabilized by H if we see it in coordinates on an adapted coframe, H coframe, then the stabilizer of this tensor in Rn it contains the group H. And we shall be interested in H structures that are completely characterized by these stabilized tensors. So this amounts to assume that your group is just a stabilizer of a collection of finite number of tensors in Rn, like this. And then Q will just correspond bijectively to a geometric structure model on this collection of tensors in Rn, meaning that for each point, there is a coframe identifying the two pointwise. Okay, so two of the main examples we will be working with is the case where H is just UM, the unitary group, when the dimension is even. And then we can just take, for instance, as this model tensor, the pair consisting of the flat metric and the standard complex structure in R2M. And for H equals G2 in dimension 7, we can just take this model to be the standard positive tree form that I told you before. And then what we are going to try to do now is to, in this language of tensors, try to understand how can you deform tensors in general to then be able to talk about flows of H structures, and then possibly, so the goal, the motivation is to, starting with a manifold that has a topological condition to admit an H structure, you want to find a suitable flow, maybe a flow, like maybe a natural choice is a flow that takes your H structure. So you consider this functional of the L2 norm of the torsion, and you want to somehow minimize this functional so that you get an H structure with minimal possible size of the torsion. And then if you want to flow structures in order to achieve such a minimal point, you would like to consider the negative gradient flow of this functional. And so before we do that, let's introduce the language of flows that we are going to use. So there's a canonical right GLN actions on tensors, of course. So where an element of GLN acts on a vector simply like this, and on a one form by pullback. And then I know how to act on a decomposable element, and so instead by linearity, you have a GLN action on tensors. And then this pointwise extends to a GLN action on tensors on your manifold. And so you get a corresponding infinitesimal action by endomorphisms, which is just to take this derivative of this exponential, where this is the action on tensors. And well, if we fix the metric G, then using the metric to lower indexes, we can decompose the endomorphism into a symmetric bilinear form and an unsymmetric bilinear form, like this. And you have some properties for this infinitesimal action. So, of course, if you act on an endomorphism, this is just going to be the Lie bracket, and the sign here you get because it's a right action, so you get a minus the adjoint action. And then the other properties are things that you might expect. So this is just a generalized Jacob identity. So if psi here is an endomorphism, again, you recover Jacob identity for the Lie bracket. And of course, if psi is a covariant symmetric or identity tensor, then this deformed guy is still the same type. The metric acting on a tensor just collects, so you just count the number of contravariant indexes and minus the number of covariant ones. And in particular, if you decompose your matrix as a symmetric part and n-symmetric part, then A acting on G is just 2 times the symmetric part. And this is simply because this is going to be this tensor here. Oh, sorry. And then if you use this thing here, you immediately see that you get 2 times the symmetric part. And so in particular, you see that the kernel of this operator here is just antisymmetric forms, antisymmetric endomorphisms, scale-symmetric endomorphisms. And and this is of course related to the fact that the stabilizer of the metric of the model of the metric in Rn is just SON, is just ON, and then the kernel of this will be just the Lie algebra of that. So it would be scale-symmetric endomorphisms. In an analogous fashion, so this operator here will, this will be a derivative of some determinant. You will get a trace here, and then the kernel of this will be just the traceless endomorphisms. So if you decompose, so if this represents the symmetric traceless ones, then you just get these plus the scale-symmetric endomorphisms. And 2 more properties here, which are, I will not use then, I think. But anyways, so now if you suppose that you have a compatible H structure, then you can further decompose.
Daniel?
Sorry?
Can I just really make a very short remark?
Yeah. Okay.
That this whole approach is strongly inspired by Spiro Karigiannis's work on G2 and spin 7, right? Yeah. So all credits in terms of figuring out this framework of infinitesimal action. I mean, this is directly derived from his original. Oh, the man is in the room.
Sure.
There we go. Yeah.
Sure.
Thank you.
Yeah, thank you. Yeah, there will be a slide, few slides after this one. There will be a slide with previous works, and I will try to give credits to people. Okay, so yeah, so if you have a compatible H structure, then you have a further decomposition of lambda 2 using the decomposition we already explained. And then, so this is the full decomposition you get of endomorphisms. And one thing you should notice is that if psi is any tensor stabilized under the action of H, then this will hold true precisely because when you act by an element since H stabilizes psi, this will be constant and the derivative would be 0. So this would hold true. And well, if you consider your H structure to be completely determined by a collection of tensors, then the kernel of this operator, meaning here that we are acting component-wise, okay? So then the kernel of this is just simply the intersection of the kernels of each individually. This will precisely coincide with H2, with the H part of lambda 2, precisely because H is the Lie algebra of the stabilizer. And of course, you can also, sometimes it's convenient to, if you take H to be, so it's convenient sometimes. So for an structure, for instance, you can consider pairs like this, the model to be a metric and an almost complex structure. But sometimes if you have fixed metric, then you can consider just the structure J, and then when you're considering stabilizer inside SON, then that's what you're getting here. So when this is like J, you have to consider this guy because this is just the kernel of the metric. Well, sometimes it's convenient to work like this if you have a fixed metric, and then the only relevant new information is you can take the metric off and just consider the additional information. And I will do so sometimes. Okay, so the upshot here is that this operator, when restricted to two forms, the kernel is precisely this H part. And so when restricted to lambda to M, this is an isomorphism. Okay, so there's a easy relation between the intrinsic torsion of your H structure and the covariant derivative of your tensor defining your H structure. And that's the relation. It's just unraveling definitions. It's really not difficult. And what you get from here is the following. So we know that this guy lies in lambda to M. And I just told you that if you restrict this operator in lambda to M, it is injective. So from here, you already get these inequalities here relating the size of this covariant derivative and the size of the torsion. And moreover, if this equality holds for elements in lambda to M, then of course from here you get directly that these norms are related by a constant. And let me just think a bit with you about this possible equality here. So if you suppose H is a stabilizer of a bunch of tensors in SON, and you decompose your H module M into irreducible non-equivalent H submodules, then what you get is the following. So when you this you can define this. Let's say this is your new inner product for elements in lambda to M. This will be an inner product because this guy is injective on this piece, and it will be actually an adding variant inner product because of the properties of this operator that I mentioned in the lemma before. So if I restrict this adding variant inner product on each of these irreducible pieces, then it should relate to the canonical bi-invariant metric by a constant. And so that's what you get here. So when you do this inner product, you get these weights, which are this constant relating the two inner products in each reducible piece. And of course, if all of these constants, these lambdas, are equal, then these two inner products are related by just a constant. But this may not be true for some groups H. And it's definitely true if M is irreducible, because then you have just one piece. But for instance, for H equals SUM, this is not true anymore. We know that M being so if you write the Lie algebra of SO to M, split it into the Lie algebra of UM plus orthogonal complement, then I can further split it into SUM plus the J0 component plus UM Earp. So this is your M1, this is M2, and yeah, so with this H, right? And then these M1 and M2 are irreducible pieces, and if you compute the lambda 1 and lambda 2, they will be different for every dimension. And so you will not get proportionality between the two inner products. And in particular, this thing here will not vanish for any element on lambda 2m. And this will be important a few slides after this one. I will come back to it when needed. But it has to do with the first variation formula for the functional we are going to consider later. Okay, so so the remark is that if m is irreducible, so this is true, for instance, for EUM, for G2, for spin 7, for the quaternionic Kähler case, and also it's true. So these are all irreducible, and there's another reducible case that is actually true also, which is the case of the trivial group, because then 8 structures are just, let me erase this. So 8 structures will be just a global frame. And so when you act with a matrix in this global frame, you will just get minus A of E1, En, and then the norm of this is just the norm of A, the norm of A. So this will be proportional, and the lambdas will all be equal to 1. But apart from these examples, you might, so for instance, for SUM, there's this problem here, and of course, for the hyperkähler group for SPK, you will have more pieces, more irreducible pieces. So at least 3 of them corresponding to each holomorphic structure, each J, right? At least 3 and some more. And it will probably yield different lambdas, etc. But, well, so most of what I'm going to talk about after this slide will be restricting to this case here. So all of these examples, for instance. Right, yeah, so you can compute things pretty easily with the UM case, for instance. So doing this infinitesimal operation, this infinitesimal action here is just doing Lie bracket in endomorphisms. So you can just compute this directly, use this squares to -1, and then you get the constant lambda here for the UM case, for instance. You can also invert this. So this relation of this guy being this, you can invert this diamond operator in this case, for instance, and get the torsion pretty easily. Okay, so next, and I think last thing I want to talk about before flows is if you take a compatible H structure with torsion T, and psi is any tensor stabilized by this H structure, then you can decompose the rough Laplacian of this tensor psi in this way here. So you just have an element of lambda 2m acting on psi and this part here. And so, well, okay, so one comment is that, okay, so this divergent, I'm just contracting the one form part here. And it's not a priori trivial that it would lie again. So T lies in this space, but takes values in this space, but covariant derivative is not a priori lying on this space, but a quick computation shows that using the nabla H minus nabla equals torsion, and the fact this guy preserves the component and the torsion lies in the right space. You can compute this, and it will be some nabla H of torsion plus a term that must lie on lambda 2m. So since this guy preserves the composition, you will get this. And In particular, if H is completely determined by a set of tensors, then you get the following. So if the divergence here vanishes, then in particular you have a very nice, so you can control the rough Laplacian of your H structure of your tensor here, defining the H structure, simply by the gradient squared. And this constant here depends on the geometry. And of course, if this equality holds, so as I was telling you before, so for H OS equal G2, spin 7, or UM, or etc., then the decomposition here is orthogonal, right? And that's because this term here is of that form I mentioned earlier. So when all the lambdas are equal, this is just C, D, C again, and you use it by invariance, and this is 0. And so this is an orthogonal decomposition of the rough Laplacian in terms of these two guys. And in fact, so for instance, in the G2 case, you can explicitly, so this guy lies in lambda 2m. And in G2 case, you can explicitly write this as S diamond psi, where S is a symmetric guy. It is actually, if I'm not mistaken, it's like this. Where this torsion here is the torsion in the G2 setting, that we transform this torsion here to an endomorphism, and this makes sense. Anyway, so this gives you a complete description of the Laplacian. So for instance, in the G2 case, as an infinitesimal action, where the A has that symmetric part and that divergent unsymmetric part. Okay, so let's talk about general flows of H structures. So we saw that when M admits some H structure defined by one or several tensor fields, then in particular, this guy here is a subspace of this kernel. And so, well, if you consider then a general GLN variation, then this should be described like this, right? So you have this endomorphism split into symmetric and unsymmetric part, and the only part of the unsymmetric one that matters lies on this part, because the other one is killed by that operator. So in particular, we saw that when you act yeah, so it's written there. So we saw that when you act with an endomorphism on the metric, you get 2 times the symmetric part. And you can always consider the metric to be part of the tensor here. And then you get this co-evolving equation of the metric. So if your H structure is evolving like this, then the metric evolves precisely with 2 times the symmetric part of these endomorphisms. And in particular, your flow would be isometric, meaning just among compatible H structures with a fixed metric when the symmetric part vanishes identically. I will focus on flows like this in a moment, but let me introduce the 2 very natural Dirichlet energy functionals. So for a closed Riemannian manifold with a compatible H structure, you can consider these 2 functionals, L2 norm of torsion or L2 norm of Nabla psi. And we saw that these guys are related by constants. And of course, if the inner product satisfies this relation, this proportionality, then they're just related by a constant. It's just a constant multiple of each other. So we will be assuming this. And then the first lemma is that if H is a stabilizer of collection of tensors and you assume the proportionality between the inner products, then for any smooth family of compatible H structures, so you give a variation, you get this first variational formula for the function. And this is, well, of course, a simple computation. So when you do that derivative of this guy, you will get integration m of nabla c psi with nabla psi. And then you just integrate by parts. You get c psi, nabla star, nabla psi. And then we had that formula for this guy, right? It was psi div t acting on psi plus torsion diamond torsion psi. And then now I use that fact that these two guys are orthogonal to each other.
Just to be clear, Daniel, just to be clear, those are the most general isometric variations.
Yeah, yeah. Mm-hmm. Yeah, so I'm computing the first variation of this Dirichlet energy among compatible H structures. So the general first variation on isometric H structures. Sorry. Yeah, and so because these two are orthogonal to each other because of that hypothesis, then you just get this, right? Kill off this term, and then, well, this is the tangent vector. So this is precisely your gradient of your functional. And then, of course, this induces a theory of harmonicity. So if you take the negative gradient flow of that functional, then, and it's just this HF flow here, this will be called the harmonic flow of H structures. And I will call an H structure harmonic when it has vanishing, its torsion is divergence free. Okay, right. So now that slide that I promised, giving people credits. So there's a lot of, so I will start excusing myself, but that there's a lot of previous literature on harmonic stuff. And this will be just a short list, okay? So this problem of fixing a metric and looking for a best compatible H structure is a node problem. For instance, it dates back to this work of Calabi and Gluck. I think this paper is entitled, "What is the best, how most complex structure on S6, right, compatible with the standard round metric?" And you can, this is a very natural question. And Chris would also formulate, so he was the guy that formulated this general notion of harmonicity of H structures, but from this point of view of sections of that twistor bundle that I mentioned before. So from this point of view of sections of frame bundle mod H. And well, in particular, these guys were pretty much interested on the case where H is UM, so almost Hermitian structures. And in this case, you can show that this DFT condition just turned out to be this one. So the rough Laplacian of your almost complex structure should commute with the almost complex structure. And of course, Kähler structures, so for which nabla j is 0, are absolute minimizers of that functional, taking the L2 norm of nabla j of t, right? But in the absence of those, there's actually also lots of absolute minimizers for this function which are not Kähler. So nearly Kähler structures are an example of almost complex structures which are harmonic. And in fact, there's this paper of Borla, Moneda, Salvai that I just recently found, actually, in which they prove that the canonical nearly Kähler structure on S6, the standard octonionic stuff, is an absolute minimizer of this functional among the structures isometric to the round metric. this actually contradicts with the previous result of Chris Wood, where he claimed to prove. So he had a series of papers in the 90s. One of them, he proved that this canonical Nilly-Kähler J is unstable for this energy. And he proves that he came to prove that there was like a 6-parameter family of directions in which you can still decrease the energy. But it seems that that was wrong. Anyways, or maybe this other. I think that was wrong. That was the conclusion. Anyways, and then that's okay. So this group of Spanish guys, they investigated this general harmonic A structures again, with a focus again on almost Hermitian structures, and they recovered some of Chris Wood results and also completed more or less the picture of characterizing the harmonicity condition according to each torsion class. So here, for instance, the Nilly-Kähler class, etc. So assuming the torsion is inside some pieces of that, he characterizes harmonicity. Okay, and then there's a bunch of, there was a series of papers on flows of harmonic G2 structures. So by Gregorian, Bagaglini, Tivivedi, Gianotis Carigianis, so Spiro. While there was also a paper by Hay and Lee. They studied the flow of harmonic UM structures. By the way, these years here, I think they are not the published year of the papers. They are probably the first version on archive years. Just to give you an idea of how things were. So in 2019, everyone was thinking about this. So there was this paper by Loubeau and Earp also investigating in general and formulating in general the general flow of harmonic H structures, where they prove, for instance, the short time existence of the flow. And I will mention in the next slide precisely the result I will need from this paper. And more recently, there are more works like in the spin 7 case by Tivivedi, sorry, I cannot probably pronounce his name correctly, Loubeau and Earp. And there's this work, very nice work of Loubeau, Moreno, Earp, and Saavedra, where they describe the harmonics sp2 invariant G2 structures on the round 7th sphere. Sorry, on the homogeneous 7th sphere. And probably maybe one of the authors in the audience, if you want to make a comment about any of those works, you are welcome.
Just say that the general flow of harmonic H structures, this should probably be the harmonic flow of general H structures.
Come again? Okay.
Because we don't flow harmonic H structure, right? It's the harmonic flow of general H structures. The adjectives general and harmonic are interchanged in the third bullet, but that's just a minor detail. But you're not
yeah. I mean, of course, the flow the flow is seeking harmonic structures. It's not a flow among harmonic structures. That's what you mean?
Yes.
Yeah. Okay. Yeah. So in the sense of the definition I gave before, right? This is the harmonic flow that will seek a harmonic structure. Right. So there's also Udav and Earp also looked at sp2, sp1 structures. So they found some examples of harmonic ones. I think, for instance, in SU3, if I'm not mistaken, this 8-dimensional manifold. They found some explicit solution for the flow on certain examples. And yeah, and then there's this work that I'm trying to talk about here with Loubeau, Earp, and Andrés Moreno. Right, so the main result of this first general theory paper of Loubeau and Earp is that we shall need is this short time existence uniqueness. Moreover, the condition for which, so first of all, so this twistor bundle here of 8 structures describing the 8 structures of M compatible with this fixed SON structure, it is, as I told you before, isomorphic to this associate bundle here. And you can then, by very basic bundle theory, correspond sections of these bundles to maps from this guy to this target, which are SON equivariant maps. And then it's not so easy to check, and then that this was work of them, that this harmonic flow that I'm talking about so far is just the harmonic flow of this map among SON equivariant maps. So it's just the harmonic flow for maps like this, which are furthermore have the symmetry of being SON equivariant. And well, this already points to something that is not likely, but that's not good. But so these homogeneous spaces here tend to have no negative sectional curvature. And we know that when the target is like that, then you expect to have singularities for the flow of harmonic maps with target space like this. And in contrast with the case where when you have negative sectional curvature, then using some classical work shows you that the flow always exists for all time and converge. Okay, by doing this bijection between these.
Just real quick, can you do it in maybe another 5 to 10 minutes? Just keeping track of time.
Just 5 minutes I have left? 5
to 10?
Because okay, maybe
okay. You do it in an hour.
Sorry, yeah, okay. Right, so from this perspective, using the known results in harmonic map flow, they prove this short-term persistence result, and further that as soon as if the maximum time of existence of a given solution for a given initial data, a given initial compatible H structure, if the maximal time is finite, then it's because the soup of this quantity here is blowing up when t goes to that maximum time. So as long as this remains bounded, the flow will exist for all time. Right. So now my goal is to give you some more precise results relating to harmonic map theory results on both sufficient conditions to long time existence of the flow and also situation where you have finite time singularity. So recapping, the hypothesis is disproportionality between these. You have harmonic flow being run, so starting at some psi 0. And one thing that you might consider is this, let's say, local parabolic scale invariant version of the energy, where you kind of make a convolution of the energy with the backward heat kernel, Euclidean backward heat kernel. So you are working here on normal coordinates on a small geodesic ball, you're choosing some cutoff function and defining this quantity. So by doing some analysis very similar to the harmonic map theory case, you can prove the following epsilon-regularity. So there's a universal constant epsilon-0, depending on the geometric data and the initial energy, such that if you control this localized parabolic scale invariant version of the energy, and you have this smallness condition, then you actually control the torsion in a small parabolic neighborhood of this point. And well, the main ingredients to prove such a theorem are these two. So for one side, you have this Bochner-type estimate. When you apply the heat operator on this energy density here, you can compute this using Bochner formula, H identities, etc. And you will get this nonlinear term here. So you have heat operator of a function less than or equal to c times the nonlinear power of this function plus something. So you cannot, so if it was linear, if you have no power like that, then you can just apply Moser's parabolic harmonic inequality and get a control like this. But when you do have the nonlinearity, then you need a control like this Monos condition to kind of do something called the Heinz trick, and then be able to use parabolic harmonic inequality and kind of treat this nonlinearity as if it was just linear. Right, and a key result to do that, to pass down estimates to smaller concentric parabolic neighborhoods, is a monotonicity formula like this. And this monotonicity formula, so the credits here goes to He and Lee, which did the same monotonicity for the case of how most complex structures. We just generalized the argument. The key steps is first to know the evolution of the torsion along the harmonic flow, and to know the Bianchi-type identities for H structures. And then it's just a matter of manipulating this expression, doing integration by parts, etc. Anyways, one key point of this is freedom of choosing any number capital N greater than 1. This is not used to prove this theorem, but it's later proved to prove another theorem. It's later used to prove another theorem. Right, so let me just prove just one thing using this, which is this energy gap. So there's a universal constant depending on the geometric data, such that if you are a harmonic compatible H structure with energy level below this epsilon-0, then you are actually torsion-free. So there's an energy gap for harmonic structures within the same isometric class. And that's because if there was no such an epsilon, then we could find a sequence of harmonic H structures whose energies are going down to 0, but they are not torsion-free, in spite and they are harmonic but not torsion-free. Okay, so right, so using this and this trivial control of the epsilon-regularity on the torsion, together with some sheet-type estimates that you can derive from the Bochner-type estimate that I mentioned before. So this sheet-type estimate controls derivatives of any order based on the control you have on the torsion. And so you get a control, uniform bound control on these guys. And so up to taking a subsequence, you use Arzelà-Scolli if you want, you get a convergent sequence in same infinity. And since the energies are going down to 0, you get a torsion-free limit. Well, but then using that estimate that I mentioned before, using the fact that div t equals 0, you have this control of the rough Laplacian of the structure by just a gradient. And then when you integrate by parts, you get this contradiction here that this term is going to 0. So you can take k sufficiently large so that this is less than 1, and this contradicts this is a contradiction. Okay? So at some point, for k sufficiently large, this started to be 0. So they were torsion-free structures. Okay, so after all, even running an isometric flow, harmonic structures are not so far from detecting torsion-free in the same isometric class. Okay, so there's this finite-time singularity result. That's the last thing I want to talk about, and I will just read the statement and give you the example. So if you start with a compatible H structure on a closed intermediate manifold whose homotopy class, so isometric homotopy class here means that when you see this H structure as a section of this bundle, you are looking at the homotopy class of this as a section, not as a map, okay? And then if this does not contain any torsion-free guy there, and the infimum of the energies inside this class is 0, then there's a universal constant so that if you start the flow with an element of this class whose energy is less than this constant, then you will reach a finite-time singularity. And let me illustrate this more precisely on a concrete example. So suppose your manifold is the flat 7 torus with the standard flat G2 structure and flat metric. Let's consider the frame bundle. This is trivial for topological reasons, but it's moreover, because you're looking at the flat metric, this frame bundle is trivialized by a parallel global frame, right? And then, okay, so G2 structures can be viewed now instead of maps from here to a frame bundle of T7 mod G2 as instead maps to SO7 mod G2, which is just RP7. And because this global frame that trivializes this bundle is parallel, you can commute the notion. So this will be a harmonic structure if and only if, so this map from T7 to RP7 is a harmonic structure if and only if the original guy is a harmonic, will be a harmonic map if and only if the structure is a harmonic structure, and it will be a torsion-free G2, it will define a torsion-free G2 structure if and only if the map is constant. So for instance, the phi 0 can be seen as a constant map from T7 to RP7. Now fix some very small radius such that using the flatness of this metric, so that this ball is isometric to an Euclidean ball. And consider some isometric G2 structure, which outside this ball is just a flat one. So it's just a constant map outside this ball. And so inside the ball, you just have a map from S7 to RP7. And then the homotopy class of this map, which is the isometric homotopy class of the G2 structure defined by it, is just an element of pi 7 of RP7. And well, this is Z. So you can choose a non-trivial element here, so that you just have chosen a non-trivial homotopy, isometric homotopy class of G2 structures, isometric to the flat metric, which is non-trivial. Okay, so fix phi this one, and then do this scaling argument here. So for each small r, you produce these phi r's, which does just this. So you scale this ball to this one. And so inside the ball, it's just this, and outside the ball, it's a constant map. Well, this is just, so this is stay inside the same homotopy class of phi, which is non-trivial. But now, if you compute the energy of this guy up to the 1/2, so 2 here, if you compute the energy here, so you use so you just use the definition and then Leibniz rule, change of variables, you get this. So this power is just n minus 2, where n is the dimension, which here is 7. And what you notice is that when r goes to 0, these G2 structures inside this homotopy class have arbitrarily small energy. So I just cooked up a family like in the theorem before. So you have a compatible G2 structure with the flat metric, whose homotopy class is non-trivial, so it does not contain any torsion-free one, and the infimum of the energy is 0. Right, so the claim here is that if you start running the G2 harmonic flow out of some of these phi r's for r sufficiently small, then you have to find a finite-time singularity. That's because the energy is now increasing along the flow. And so if you assume this to be very small, so we start with an R very small, then epsilon-regularity with sheet-type estimate, assuming that the flow would exist for all time, would give you that the flow actually converges, and it would converge to a divergence-free torsion G2 structure inside the same homotopy class, but with a very small energy. So if you choose R very small, then you are below the energy gap result, and so this should be a torsion-free guy. But you cannot find a torsion-free guy in this class by construction. So that contradiction gives you the finite time singularity. So the flow has to stop at finite time. And what you observe further is that in this example, although these phi r's have arbitrarily small energy, the L-infinity norm of the torsion, you are concentrating it more and more, and this is exploding. So this illustrates that if you want to get some long-time existence result, you just, with some smallness of initial energy, you have to consider this smallness to be with respect to how big is this L-infinity norm of the torsion. And that's the last result. So this is the analog of Chen-Ding for harmonic maps. So we start with a closed-oriented Riemannian manifold admitting a compatible H structure. So if there's an epsilon, universal epsilon, such that if this guy is bounded by, let's say, K, then there's a smallness based on K, and this is like growing. So I think it's something like arctangent of 2K squared. Oh, no.
Daniel, we need to wrap up.
Sorry. So yeah, so this is very small if K is very large, right? Then the flow will exist for all time and converge to a torsion-free G2 structure, H structure, sorry. And maybe I will stop here, and if you have questions, I can tell you something more. Sorry for blowing up the time.
All right, let's thank the speaker, please. Since we're a bit over time, can we just have one question at most? Speaker has to leave. All right, catch you later. Are there any comments or questions? One comment or question? Or if not, I can always contact Daniel and pick it up from here privately. There's a lot of content in this. I mean, there's a lot of material he wanted to show, so I understand we went a little bit over time. All right, in that case, let's just thank the speaker again, please.
Yeah, thank you.